I'm Charles Clark, here to introduce Marianna Safronova, a collaborator of mine of long standing. I've known her probably about 20 years. She got a bachelor's and master's degrees from Moscow State University and a PhD under the supervision of Walter Johnson at Notre Dame University. Did a postdoc at NIST and was quickly appointed by the University of Delaware, I think in the year 2003 or something like that, where she's a full professor now. Marianna is, in my opinion, if you name the top 5 people in atomic theory, she's going to be on the list. She's transformed classical first principles atomic structure calculation, made it a valuable tool for the sort of precise spectroscopy, and particularly spectroscopy of intensities and oscillator strengths and level shifts that's most important in the cold atom community these days. She's collaborated with many people here at JQI and at JILA all across the world. You'll see some of the results of her research displayed in her talk today. She's an adjunct fellow of JQI, one of probably only 3 or 4 that we've ever had, and she's certainly our longest serving. One thing to note about the Safronova family is it's full of physicists. Marianna's mother is a well-known, let's say, classical theoretical atomic spectroscopist. And I've actually co-authored a paper with Marianna and her mother, which is something pretty unusual, I think, in our field. So without further ado, please welcome to the JQI seminar today, Marianna Safronova.
Thank you so much for the invitation and for introduction. Can people, I don't know if I should ask if people on Zoom can see and hear me. I assume they would.
Sounds good.
Okay. So I will talk mostly about the clocks, but I will talk about a variety of other subjects. And as Charles said, I'm an atomic theorist. And as an atomic theorist, it's always good to ask question, what are really the big picture vision here? What is that we're actually trying to achieve? Let's say not in next year or maybe next 5 years, but sort of, next decade or so. And here we have 2 really big picture questions. Okay, that worked before, but it does not work now. Okay, a moment for technical, okay. Okay. So if I think about asking big picture questions, and I'm sure there are many of you have many different big picture questions, but the 2 of the ones I'm particularly interested in myself, it's first, how to maximize the potential of AMO technologies, our various, loosely labeled things called quantum sensors, to discover new physics. And in our case, quantum sensors are a very broad variety of things. All of your various atom traps are perfect quantum sensors. And when we talk about discover new physics, what we actually mean that it's something which is not this. So anything beyond what is on our standard model. And the second question, which is actually sort of related, it might not look like it's related, but it is related, is to, okay, I think we're still having problems with, okay, let's try. Okay, it works now perfectly. Thank you so much. Okay, it's to how to accurately calculate a wide range of atomic properties in anything of the periodic table. So here we have kind of our standard model, and here we have our atoms and ions. And the question is not only how to accurately calculate it, of how to make our calculations available to all of you. So essentially with an ease, it's not like, okay, we have a code online and you can, download it and eventually want to run it. But how can you essentially get the data in a manner that if you send me an email, like for example, what is this matrix cell in rubidium, how is it you just go online and get it? And that's a kind of our other life here of how to do this. I will talk a little bit about this project. Obviously, neither one of those is a solved problem. So this is our big picture vision, and that's many projects which we have related to both of those things. These questions are related because very frequent question in terms of maximizing this potential of AMO technologies is, I have an idea for the experiment. What is my best atom or molecule to use? And generally, to answer that, you need to know the properties of atoms. So big picture questions about our universe. Let's start with the first one. Okay, there are many big picture questions, but nevertheless, let's focus on some of the largest elephants in our room here. And one of those, it's a missing matter. And this is a weird fact that if you actually do a lot of astronomical observations, all of those on all the scales from the earliest universe to our galaxy will tell us they're missing 85% of all matter. We don't know what it is. We are absolutely certain this is not standard model. And that's pretty much all we know about it. We can, we ruled out a number of things. I mean, there's not just, black holes, Jupiter-sized planets. They're not standard models. They're not standard model objects. And then also we have observations which are saying that universe is expanding at accelerated rate. And again, there is nothing in the standard model which explains this. And that's, we kind of label it dark energy. Let me say we know even less about dark energy than we know about dark matter. That's been around for the past 20 years. There are numerous astronomical surveys, and they all see that, and we also do not know what that is. And then, of course, if you have some unknown matter and some unknown energy, it's most likely not interacting with the standard model via the fundamental forces. Of course, dark matter interacts via gravity. The question is, how else does it interact with the standard model? And that's most likely through some different sort of mediator, so they're probably different forces. So occasionally the search for dark matter is essentially the search for a fifth force. And then we also have a very big problem, and this is one of the largest elephants in the room. I mean, look around, there is no antimatter in this room, at least in not any measurable quantities. So somehow during the Big Bang, the matter and antimatter was produced, and it's supposed to be, according to standard model, produced in nearly completely equal quantities. So if our universe was a standard model, it would not exist. We will not exist. This is not a small problem. This is a monumental issue here. We do not have explanation for that, why all matter and antimatter did not annihilate and just left us the universe full of radiation. That's what should have happened. It did not. Somehow, for every billion of your particles, there were antiparticles, there was 1,000,001 particle, and that's when it's annihilated, that's one particle was left out of 1 billion, and that is much more symmetry that standard model will predict. And again, we do not have a solution for that. And then the last thing, it's a hierarchy problem, and it's actually a very serious problem. So if we now know what the Higgs mass is, we know what the vacuum expectation of Higgs field is. We know that the Higgs gives masses to particles. And that number, the expectation value for the Higgs, is very unnatural. If you start with try to model all possible universes, you will not come up with ours. You end up with either all the masses as 0, or the Higgs field is fully on, and then all masses are essentially, or all particles are so heavy they go above the Planck mass, and at Planck mass, all particles are black holes. Again, we will not be here. And mathematically, that problem reduces to essentially impossible cancellations of very large numbers at all the energy scales. So as a physicist, I don't believe in many digit numbers canceling exactly just because accidentally. So there has to be some reason for it. And people have been looking for a reason for it as well. So today I will mention the 2 of those specific problems. So the best case scenarios for dark matter, what everyone is searching for, solve more than dark matter problems. They solve some other problem as well. That's why WIMPs are so popular, because they solve the hierarchy problem, and they have also relevance to the matter-antimatter asymmetry. And that's what axions are also favorites, because they solve a strong CP problem. It's not in here, but it's also a problem we don't understand. Now, if you're interested and would like to learn more beyond this talk, there are new resources. You may have seen this one. So this is our fairly recent review that's about 3 years old. There's only almost 1,100 references in there. Try checking 1,100 references from 6 different causers. So, but almost all of these references are past 10 years. So there is enormous effort in AMO search for new physics. And Charles also won the author of this paper, so you can always ask him as well, since he is here. And then there is a very recent and still ongoing new effort. So Dima Butker and myself organized a special issue in Quantum Sensors for New Physics Discoveries. And Quantum Science and Technology Journal, which is a new flagship IOP journal, it's supposed to be above the New Journal of Physics. They let us do a very different special issue. So those things are not just like, okay, we've done research and here is the result. Those are new proposals, what's going to happen next 10 years. And we do have 17 papers so far in the issue. There's still papers being processed through it, and they're on very different topics. They are all different AMO type technologies for new physics searches. And they range from dark matter, EDM, gravitational waves, and many interesting things. Quantum gravity tests, that sort of thing. We also have an interesting editorial, which you may check out, called Quantum Technologies in the Elephant, where we actually dare to define what quantum sensor is. Okay, and now I will, for a while, I'm going to just talk about clocks. And clocks are exceptional. First, clocks are beautiful dark matter detectors, which are built for totally different reasons. It's like it's great talking to particle physics, like you already have a detector, you don't have to build it, it's there. It's going to continue to be there. It's going to be, you'll have networks of clocks, you'll have clocks in space, you'll have beta clocks. So it's something which already exists. It exists for applied reasons of metrology, and it's going to improve. And the reasons why clocks are so exceptional devices for new physics searches, it's because these are some of the probably the most precise devices on Earth. They can measure now frequency to 18 significant figures. And just to put this in perspective, because it's such low numbers, you don't have a feeling for what it is. This clock will not lose 1 second in the lifetime of the universe. That's what 10 to the minus 18 means. It can also detect a difference in height of 1 centimeter. You take your optical table with a clock, you put it 1 centimeter up, it will start ticking differently. It can detect gravitational redshift at that level, which is amazing. Therefore, if there is some new physics which shift your clock frequency, you can actually detect it. And you can detect it because there is enormous effort in understanding systematics of these clocks. Because in order to prove that you're accurate 10 to the minus 18, you check everything which can affect your clock at that level. So in this case, if you see new effect, and some of the new effects actually have a very specific signatures that can be attributed to new physics. I also would like to point out that our general postulates of physics are not tested at that level. When we say, for example, that we have Lorentz invariance for electrons, the best limit is established with clocks, with the terbium plus clocks. So meaning if you rotate your experiment or you boost it with a certain velocity, laws of physics should not change. This is actually a postulate. It needs to be experimentally tested. And the best limit for electrons actually is clocks. So not only those things can help us search for dark matter, that can actually can test fundamental postulates of physics, the equivalence principle. So now, clearly not all the new physics will change the energies, because the only way we can see new physics if it changed atomic energies. So the question is, which new physics changes atomic energy and therefore the clock frequencies? So by the way, if anyone here has a question, I will, or actually in Zoom, please ask now, because I will switch between 3 different topics. So I'm happy to ask questions, answer questions during talk.
This is Alan Migdal. Can I jump in with one?
Of course, absolutely.
You mentioned that, I think you said that the matter-antimatter asymmetry was a part in a billion, which was beyond what the standard model allowed. What level does the standard model allow for that asymmetry?
I can't come up with this number right now. I can check it, and if you send me an email, I'll make sure that I do. But it's by many orders of magnitude smaller than this.
Okay, thank you.
So, and this the standard, the CP violation does arrive in the standard model, but it's not enough for it. So you need violation of CP when you switch charge and parity, and in this case, it's present in the standard model, but it's much lower level. But in terms of number of ratio of particles, I'll find out. It's a good, actually, very good question.
Okay.
So,
Thanks.
but we are orders of magnitude there. Charles?
I mean, there are already problems enough, but you haven't mentioned gravity. Is gravity completely outside the sphere of things that we can consider in terms of precision atomic metrology?
So Charles Clark asking, what about gravity? Is it completely outside of what we can actually measure with precision metrology? No, in fact, the gravity is actually, I haven't put gravity in there, but for example, atomic clocks can be used to test GR. And also we can look for gravitational waves with atom interferometry or actually with atomic clocks in the future. And yes, the problem with gravity is it's one of the big deal. Gravity is not quantum. Gravity and quantum mechanics so far don't, okay, there are many possible theories, but we don't have a full complete theory of quantum gravity. And that's a big question.
Perhaps that's a subject for your physics colloquium tomorrow.
I will talk a little bit about new ideas for gravitational wave detectors tomorrow. So the question is whether there is a talk colloquium tomorrow, was I'm going to actually be talking about it. I'll talk a little bit, but that special issue has actually papers about this. So the ones which I showed on the previous page. Okay. A very brief introduction how atomic clock work. You probably all have seen it before, but just in case. We are going to have a frequency standard. So this is the clock has essentially 3 parts, okay, main parts, and from a standpoint of view of theories. So sorry. Okay, this button. So you need a frequency standard, meaning you need some perfect oscillator. Atom and ions are perfect oscillators. They're all the same in the same environment. So we take for ions, so far all clocks are operating with a single ion. Aluminum plus needs a second ion as a sympathetic cooling and probing ion. Lattice clocks can operate with thousands of atoms, but this is your frequency reference. So you pick a very, very narrow transition. And meaning that the upper state lives for, you want like 100 seconds, it could be 20 seconds, or it could be hours. In case of Ytterbium plus, it could be years. So a very narrow transition, and that essentially the frequency which you want to, that is your frequency standard. Then you build a laser, and it's a very, very special laser, which interrogates the frequency standard at that frequency. So you would like to be able to tune the laser exactly in resonance with atoms. So what you actually measure, it's atom population in this case. So what you want to essentially end up which transition, which laser frequency do you need to make the maximum probability of the atoms actually jumping from 0 and 1? Technically, you do actually pilot rotation, so you actually get superposition of zeros and 1 because it's just easier to then tweak your frequency afterwards. But as soon as you're happy with what frequency you have, you actually count this frequency with optical frequency comp, and those clocks are more precise than the standard of time, which is cesium. So generally, right now, what you can do, you can compare 2 different clocks to the same frequency comp. So you can compare those ultra-precise clocks without actually referencing the second. It will eventually be redefined, and there is a plan how to do it, but it's going to be, quite a few years yet. So this is a basic idea of atomic clock here. The important point that this laser, it's an ultra-stable laser, because when you actually probe the atoms, if you then, don't talk to the atoms, the laser will go off phase and off frequency. So what you want ideally the laser to be able to actually maintain phase and frequency without talking to the atoms for as long as possible. Right now, the record is about 5 seconds or so, which is amazing, actually. Eventually, it will get to 100 seconds with special cold silicon cavities, and that's probably where, in this case, the cavity itself can actually serve as a frequency standard. Yep.
What's that feedback time? Less than 5 seconds.
Okay, so the question here is not what you want ideally to do. You would like the clock to operate continuously. You want no dead time. So in this case, the probe time, it could be in micro, it actually varies significantly depending on which clock it is, whether it's ion or atom clock. So ideally, what you want operating it continuously. And in this case, you have about 50% dead time when you actually don't talk to the clock. There is a simple reason, just make 2 of them. So if you talk to two, that's been demonstrated, the zero dead time clock had been demonstrated. You have two atomic ensemble. So while you're cooling and preparing one, the laser talks to another one. And then you do pivot to pulse, you wait. Again, you could wait for seconds. Generally, they right now don't do it, but you could generate probe time is smaller than this. And then you just talk to the second sample. So you could do it in principle. But actual protocol varies depending on the type of the clock and the kind of your laser. There are many other ways to actually go around the laser problems. For example, if you have one clock which ions live for very long, and then you have a lattice clock with superb laser, you can actually do a correlation spectroscopy that you actually tweak the phase of an ion clock based on lattice clock because it's much more stable. So that actually allows you almost, I think, there was a NIST experiment. You could actually get to 10 to the minus 16-ish for the ion clocks, or even better, which is amazing.
Marianna?
Yes?
This is Bill Phillips.
Mm-hmm.
So since you're getting into the nitty-gritty of how these things work, even talking about the Dick effect, I'd like to ask you about whether there are issues having to do with the asymmetry, the possible asymmetry of noise in the laser. When you look at the picture that you showed, you have to split that line to, somewhere on the order of part in 1,000 or even better. For cesium clocks, they split it to a part in 1,000,000 in order to get the kind of precision and accuracy numbers we're talking about. How sure are we that the noise on the laser doesn't have a part in 1,000,000 asymmetry?
So the first, you can actually model the laser noise. In fact, we actually have a code to model laser noise because you need to, if I'll talk in the future about dark matter, you need to extract it on top of the laser noise. So I think first it can actually be probed. For example, you can do dynamic decoupling sequences to perhaps measure the laser noise. And again, I am a theorist here, so I believe in the case of you actually start dealing, so I've seen profiles of laser noise. I think I would assume that's measurable, but perhaps somebody from experimentalists here on the Zoom will correct me. So I think that actually with dark matter, you need to know what your laser noise is. But it can be modeled, or presumably it can be measured specifically. So I think if there is I think it's not the issue of asymmetry. I think there's issue of various peaks in laser noise at various frequencies, just because you have various devices. So there is various noise, which I believe is reasonably well understood.
Okay.
Okay. So in terms of searches for new physics beyond the standard model, there is quite a few of them. The oldest one probably just a question of whether fundamental constants are constant. Then tests with the equivalence principle. Essentially here, the Earth actually moves on elliptical orbit. And by the way, it's an interesting question. Are we closer to the sun or further to the sun in the North Hemisphere during the winter?
Closest.
Yes, and that's quite amazing, actually. We're actually closest to the sun during winter, just the way the North Hemisphere is, and that actually does affect climate. But nevertheless, it creates a variation in gravitational potential between June and July, which clocks feels, and you can actually measure what that is. So then you can actually do a absolute test of GR if you put clock to space, and you can actually measure the redshift to extreme precision, much better orders of magnitude than anything's been done by any other probes. Then recently been recent improvements in searches for violation of Lorentz invariance. That was with 2 terbium plus clock. The beautiful thing about this particular experiment, all they did, they had 2 terbium plus clock because that's what meteorology institutes do. They have multiple clocks. All they did, they just put magnetic field as perpendicular as possible and operated the clocks for 6 months. So, and that is exactly the beautiful thing of those experiments, because that's what meteorology does anyway. And you can extract the best, they improved it by 100 2 orders of magnitude, by factor 100 from the previous tests. And then there have been proposals for the gravitational wave detection with atomic clocks. And I just heard beautiful Peter Graham's talk about clocks on asteroids for gravitational wave detection. And that's just fantastic, fantastic to see the future. So now, specifically about dark matter, as of now, we don't have a good idea how, for example, detect axions. Axions are pseudoscalars with clocks. Magnetometry experiments actually do it beautifully, and there's all the microwave cavity experiments, but the clocks are sensitive to the scalar dark matter. And because the scalars will actually affect the energy levels. And the question is, let's say you can measure changes in atomic nuclear frequency. Let's be optimistic, 19, 20 digits. Okay, we are kind of at 18 now. And that also, your dark matter can solve some other problem. So that's kind of your bonus question here. So now, first, where do we take dark matter? It's everywhere. If there's a heavy WIMPs, there are about 2 of them in this cup. If they are ultralight scalar particles, there are very large quantities in our room. So idea of detection, the dark matter is just present in our galaxy. It's present in the solar system. And we are just moving through the dark matter with Earth at about 230 kilometers per second. There's a little bit of differential in winter and summer just because of the Earth goes around the sun. So the dark matter is just here to detect. And we have no idea what this mass is. And when I say you have no idea, the level of ignorance is incredible, because from this side, if we're actually talking about 100% dark matter, that eventually we get about 10 to the minus 22 electron volts. Anything lighter than that will not bind a dwarf galaxy. So you're getting to the characteristic length of galactic scale at this point. And anything which is heavier than Planck's mass, okay, let's not count that a particle at this point. So it's a black hole. Okay, there are many various composite things, like, for example, primordial black holes, which are heavier than this, which could be dark matter. But if you're talking about particles, then that's a lot of orders of magnitude here. Now, clocks are specific, and all the quantum sensors are mostly looking for ultralight dark matter. There are a few exceptions. There is, of course, beautiful proposals here to use knowledge of vacancies to search for essentially to use diamonds to search for WIMPs, and Ron can elaborate more on that. And there are some efforts looking for sterile neutrinos with cesium traps. There is a Hunter experiment in UCLA, but most of those actually focus in ultralight so far. And specifically, clocks are sensitive just from characteristic clock scales at something about which is lighter than 10 to the minus 12 eV. So the first thing that it has to be bosonic if it's light. Fermionic dark matter, anything less than 10 eV, will not be bound by our galaxy because, well, your Pauli exclusion principle then tells you that you impart such velocity that is going to leave our galaxy, period. You just can't have that many fermions. So then, how would we detect our dark matter with clocks? So the main reason, if dark matter is that light, per Deborah volume, there is a very large number of them. We are talking about very large occupational number. So we are not detecting dark matter here as, you know, your dark matter particle hits your clock or atom or whatever it is. It's just interaction of your atoms with the coherent wave. It's just cosine wave. It's just a classical wave. And the question is, what's, of course, the frequency, and that's your Compton, it just relates to your Compton wavelengths for dark matter, and there is a velocity differential of about, 300 kilometers per second there, so there's some spread. So it's sort of coherent, and okay, we can discuss whether it's coherent or stochastic, that's a whole different topic, but for most purposes, think about it as something which Q factor about 10 to the 6. And just because V divided by C 10 to the 3, and your Q factor goes as V squared, so 10 to the 6.
So it's a wandering phase.
Yeah, right. So it's quasi-coherent, meaning if you actually, in certain cases, you want to be within more than one coherence volume. Otherwise, your actual sensitivity drops. By how much it drops, there is, of course, paper on the archive, and I know it's published yet. It doesn't drop by a factor of 10, but probably by a factor of 3. So you probably want to be through the few coherence volumes. Okay, so bad news for everyone, you just have to sit in the lab longer and wait for it. So in this case.
Is it established that dark matter is bosonic?
No, so the question from Charles was, is it established from dark matter is bosonic? No, it can be fermionic or bosonic, but if it's ultralight, if it's below 1 electron volt, it has to be bosonic, because the fermionic dark matter cannot bind galaxy because the Fermi escape, your Fermi velocity is larger than escape velocity for the galaxy. Okay, but yeah, and also, I mean, the universe is fun. There is probably unlikely that dark matter just one particle. There's probably a whole dark standard model out there. So we could have bosons, fermions, we could have, newly charged particles. Probably won't get to them, but if I do, I can talk about that as well. So now, what kind of effect do we have? So what is it our signal? So dark matter field, which is your just cosine wave, will couple to electromagnetic interaction. And when I say couples to electromagnetic interaction, imagine your F mu terminal Lagrangian we all know and love, multiplied by a cosine wave. That's your extra term. You can multiply by phi or by phi square. You could have linear interaction, quadratic, but just let's say it's linear because it's a first order effect. So what it will do, you are actually getting oscillating thing multiplied by your F mu tensors. So, and this is a term which is essentially your redefining your interaction of electromagnetic interaction. So oscillating terms will appear in Lagrangian. So that means the fundamental coupling constant, meaning the alpha fine structure constant, will oscillate. All of mass ratio will oscillate. It will couple to Dirac terms and for electrons, for example, as well. So then, if fundamental coupling constants oscillates, remember, all the atomic energy level are proportional to Rydberg. So they're proportional to alpha square, where alpha is fine structure constant. So that becomes oscillating. And then therefore, if you just detect the ratio of clocks and monitor it over time, you can detect this effect. Why does it work? It's because not all clocks are the same, have the same sensitivity to alpha. So what you do, you pick one clock which is sensitive and one clock is not sensitive. A very easy way to distinguish: anything light is not particularly sensitive. Alpha is relativistic effect. So compare a light and heavy clock. Ytterbium plus octoball transition is special. F electron shell is collapsed. It sits much closer to the nuclei. There is enhancement in there. Okay, if you only have one clock, you can compare it to your cavity. Because the cavity, you have a length of the cavity with fixed. Length will vary as alpha, but clock will vary as alpha squared. So you have effective factor of 1. So now this is the best limit. This is the most recent Gilly limit. And by the way, this purple line, this is a mission, microscope mission in space. In space, read much more expensive than the clock. And then the green is a projection which you could do with strontium cavity comparison. But the main question is how you can do orders and orders of magnitude better. And there we actually come to the question that can also you do orders of magnitude better, and can you solve some other problem? And just sort of this revamp of the hierarchy problem, it's a very serious problem. It's while pretty much Large Hadron Collider was built to solve it. If you summarize, if you have any particle physics in the audience, you can correct me. And because the main idea, we thought we will see supersymmetry, because supersymmetry is such a beautiful, beautiful way to actually solve the hierarchy problem, and also the matter-antimatter asymmetry. So very simply, to each boson you have a fermion, to each fermion you have a boson, and we were supposed to produce, hopefully, those particles Large Hadron Collider. We did not see them, which is a problem by now. And there are other ideas of how to solve the hierarchy problem. And there is a dynamical explanation relaxation, where actually you do not have anything which Large Hadron Collider can see. What you could see, you actually end up with the extra ultralight particle, the relaxion, which is a light spin zero field, which will roll actually with the Higgs. And there is a back reaction between the relaxion and Higgs. It will stop the Higgs field at this unnaturally low value. And we collaborated with Gilad Perez's group, and we actually pretty much found that the nuclear clock could actually probe the relaxion parameter space. It's actually fairly similar space to somewhat below the natural light scalars as well. Okay, so how to significantly improve new physics tests with clocks? How much time now? Okay, so what is it, like 10:30 now, or?
Yeah, it's 10:35.
Okay, perfect. So how to significantly improve new physics tests with clocks? The first idea is to actually improve clocks, and that will happen. There's no doubt that clocks can be improved by orders of magnitude, and there is no fundamental reason why that can't happen. The second thing is you can build new dedicated clock with high sensitivity to variation of fundamental constants. And in this case, if you look how sensitive current clocks are, I mentioned ytterbium plus is only one with -6, cavity is 1, strontium is 0.06, ytterbium is 0.3. Okay, and this factor, this dimension, this factor actually go directly transforming your sensitivity in your clock to, in a frequency measurement to sensitivity and alpha variation. And there are proposals of how to do better. Yes.
So I have a very general question. So the clocks are so sensitive now that sort of it seems like your neighbor moves an optical cable and the clock frequency changes. So it seems like we're getting to the point where somehow the quantity being measured is not really well defined, because it depends on all of, is there a new building down the block? Okay, the clock frequency is different now. And so like, what does a couple more digits of precision mean when it now depends on cars driving by and somebody parked a truck outside?
Okay, so the question is, the clock precision, it's so great that actually things around it, for example, okay, you do have a large mountain and boulder nearby. Eventually, I mean, the question is, for example, if a truck goes nearby, optical table move, that can be detected. So, and yes, there is environmental dependence of frequencies, but it's not a bad thing, it's a good thing. And it's a good thing because now you can actually put clocks in space and they will measure gravitational potential of Earth. And there is numerous proposals of how to do it. You can put gravimeters. Yes, you comparing clocks on Earth. For example, you can avoid all of that if you're comparing two ions in the same trap. So for dark matter experiments, it's not an issue. There are technical ways around it. More than that, there are actually ions with, or actually neutrals with more than one transition in the same system, and you can compare them. So there are, for dark matter detection, there are specific cases which you can actually use. But generally, I know John Yee has this new paper on arXiv, and there you can actually eventually, I mean, not yet, but eventually you'll be able to actually see differences in gravity between different lattice sites, which is amazing. So that's actually incredible quantum many-body simulator, and it's also applied physics device to actually model Earth's gravitational field as well eventually. Yes.
Of course, people do differential measurements too. You have more than one type of clock.
Yeah.
Semi-collocated, sensitive, both sensitive, in similar ways to gravitational variations and potential and whatnot, but differently sensitive. That's Marianna's point, of course, that she's getting to here, to the new physics of interest. Sometimes we do want to map gravitational potentials just on the Earth. It can be useful, as she's saying, but sometimes we would like to be insensitive to that, so we can correct for it through differential measurements.
Okay, so as was beautifully pointed out, as I said, the interest in differential measurements, and there is also idea that you can actually connect different clocks by having a clock on orbit as well. And also there are gravimeters, which can also allow you to measure gravitational fields as well. So this is not as bad issue as, for some of the other precision tests when you actually really need to know, like big G measurements, you really need to know gravitational potential there. So, yes?
How do you control the sensitivity experiment? If you want, what do you change in your setup if you want a more or less sensitive clock?
So the question was, how do you change sensitivity in an experiment? Want more or less sensitive clock? You want different clock because you're measuring the ratio of the frequencies. So you want one clock to be not sensitive or one clock being sensitive that maximizes your effect. Or sensitivity can be either positive or negative. So, but in this case, sensitivity is fixed to your atom. So there is really, it's those numbers, first we compute them with very high accuracy, we know what they are. So we do know that out of every operating clock, ytterbium plus ocupole transition has sensitivity -6 and nothing else does. So if you want the most sensitive test with current clocks, that's the one which you want to use to something else. So in fact, there is a ytterbium E2 transition, which has sensitivity +1. So you can just do 2 clock measurements, which was done. before. So unfortunately, you cannot affect sensitivity during experiment. It's fixed to your atom. You could use different atoms, or you could use nuclei. And that's my next topic. So the one idea which we are pursuing, it's a nuclear clock. And there is a new review, which is also our ERC proposal. And also the next thing is a highly charged ions. And highly charged ions were completely separated from ultra cold community until very recently. And now they're actually ultra cold highly charged ions. The first quantum logic spectroscopy demonstration was PTB. If you have not heard Pete Schmidt's talk, it's online. If you're not sure where it is, send me an email, I'll send to you. It's a fantastic experiment. It's 10 to the minus 15 precision with a highly charged ions for frequency at this point. Okay, so highly charged ions. First, the thing is small. So when you have neutrals, you have your atom, electronic cloud. When you actually start tearing away electrons, it shrinks. So electronic cloud shrinks and shrinks and shrinks. So it's a much smaller thing. It's much smaller affected by electromagnetic fields just because of it, because there are smaller moments to deal with. And eventually a highly charged ion, fine structure or hyperfine structure will become optical. And that could be served as a basis for clocks. But generally, if you have M1 transitions, it's maybe not such a long-lived line. But there are optical transitions which are extremely long-lived lines. For example, there is M3 transition, at least like 20 million years. So there are all these kind of varieties of different types of clocks. Do you have a question? Okay, sorry, okay. So just a little bit about highly charged ions. That was the first experiment in 2015 at Heidelberg. And that was, they actually injected, you see those large blobs, those are argon 13 plus ions, which are injected in beryllium plus crystal. And then they melt the crystal and left with one beryllium plus and one argon 13 plus. There's a next experiment at PTB. And they actually, that was the best frequency measurement, 10 to the minus 7, and they went right down 10 to the minus 15. Imagine experiment to improve any experiment of this type by 8 orders of 8 orders of magnitude in a single measurement. It's because now it's ultra cold. So this technology now exists, and this is our proposal for California 15 plus. And before you start saying, oh, no, it's reactive. Well, a little bit. Okay, and again, you need one ion, okay, maybe a few ions. And actually, it's really not that radioactive. So it's about 1,000 years, 900 years half-life for 1/2 isotope. Everyone, I know quantum information loves 1/2 spin for the isotopes. Here's one. And that would have to be, of course, produced in some sort of a nuclear facility, but it's sufficiently long-lived. And sensitivity of variation is 110 if you actually have 2 of those ions in the trap. So, and we have an extremely detailed proposal about how such clock, what systematic effect such clock would have. Remarkably, actually, people got money of that in UK to actually start work on this. So this experimentally will happen. And then nuclear clock. Okay, why are we talking about atomic transitions? Why not nuclear transitions? Well, because nuclear transitions are not laser accessible. Well, because they're usually MEV, that's the energy in EV for the nuclear transitions. We do not have KEV or MEV high precision lasers. Here are the clock frequencies, and surprisingly, there is this one nuclei. So this is just, a white rabbit here. There's only one nuclei which has laser accessible transitions. They haven't found any others. So the idea here that you actually have, okay, maybe it's not perfect. This is about 150 nanometers. That's an average of 2 values. And I'm a part of the ERC synergy collaboration to build 3 of those nuclear clocks and test fundamental physics for this. If you're interested in review an ERC synergy project plan that's just been recently published in the special issue. As of now, as you see, it's very ambitious. The idea is to go from 2 significant figures to 15 significant figures in 5 years. But we have a very good idea how to do it. And the reason why we want to do it, it's because if you just do, even hand-waving arguments of why nuclear clock, because your frequency for that transition is 8.2 eV, but you're different in the Coulomb energy scale, somewhere MeV-ish, just because your energy itself is a GeV, 10 to the minus 10 to the 9. As again, we do not believe in accidental cancellation to 9 significant figures. So there is possible 4 to 5 orders enhancement. So enhancement factor 10 to the 5. So your clock at 10 to the minus 19, your alpha variation 10 to the minus 24. And it'll be very hard to get 10 to the minus 24 with strontium, for example. So it may be possible, I don't know. But again, here you just have a clock for free. Sensitivity. There is a proposal how to actually measure the sensitivity. This is a fairly controversial nuclear physics of what that number actually is. The idea is that you actually measure probe the difference in Coulomb energies between two transitions. And of course, where does the difference in Coulomb energy come from? First, your radii is slightly different when you excite the nuclei in excited state. And then your quadrupole moment is slightly different. And then, of course, you have electro-octupole moments. That's been checked that it's probably not significant. And there've been a measurement of the hyperfine structure of isomer, but it's not yet precise enough to actually infer that number. There's been an effort to infer it in different ways. So it's fairly large. So it's supposed to be still very, very large. And again, here, that's not EDM. You don't particularly care exactly how large it is. It's being large means you have much higher chance to seeing the effect. You don't need to know exactly how large it is. It's just the enhancement factor. It doesn't really go into any dark matter computation except the projected sensitivity of your clock. However, of course, it's very important that we actually understand the system extremely well from which we're building a clock. So we've been working on developing new methods for theoretical computations for those systems. And the actually magnetic dipole and electric quadrupole moments of thorium nuclei come from the combination of Alex Kuzmich measurements and our computations to about, sort of couple of % level. The question is, can you do better? And we have developed a new method when we actually have full couple cluster methods, all core triple and valence triples included. And here is comparison of the energy of thorium 3+ states. So we can actually get absolute energy to 0.3% in something as complicated as thorium ion. And the difference between the ground state and excited energy, you see it's somewhere between, better than 0.1% and 0.3%. So this is new calculation, it is on archive. And that's because now we actually have core triples in computation, which it used to be thought computationally unfeasible to do that. And the whole point was to establish the nuclear moment. So the question is, it's not just what the numbers, it's what the uncertainty is. And we found that accuracy of our understanding of electronic correlation is no longer a defining point here. So the main point is that we actually don't know the nuclear magnetization. And it can be measured, it can be probed, but it's fairly complicated. So we actually done some modeling based on existing experiments, and we found that it could be uniform, but it may not be. So this is actually defining a limit of our accuracy here. And for the quadrupole moment, this problem doesn't exist. So we actually recommend quadrupole moment. Okay. So when you have a nuclear magnetization, it doesn't have to be spherical. It could be complicated. It could be some oblong weird thing which you don't know. For example, in gold, it actually was shown that it could be extremely non-uniform. So it's just not known. That's a Bohr-Weizsäcker effect. So you don't know what the nuclear magnetization is. We assume it's a charge distribution, but it's not.
That's very relevant also for
core
atomic
right.
structure too, I guess.
Well, it doesn't really affect the energy levels. It will affect the hyperfine constants, but it's too small effect to affect the energy levels. Atomic energy levels are pretty stable with, there are some special effects, but not at this level of precision. Electronic correlation with swarm everything here. So. And then another new computation, the question is, people are still have not excited this nuclear transition by a laser. And the reason, because it's a very weak transition. We're talking about a lifetime of more than 1,000 seconds here. Could be 10,000 seconds. So all the measurements of the transition energy were done actually through the electrons. They were not done through the laser excitations. So one idea from Adrian Palfi's group to actually use highly charged ions for that, because there is accidental degeneracy with a nuclear transition in thorium 35+. The question was, how precisely was that known, and can you guarantee that it's actually close to the nuclear transition? And we've done this enormous computation. We have this new message passing interface, parallel configuration interaction code. We can run 100 times larger problems than we did before. And we actually found that it's actually very close to the nuclei, projected energy. In fact, the uncertainty in actual measurement of this nuclear transition energy dominates at this point. So, but nevertheless, we have new ideas of how to actually measure those and compute those things. So, and then I have a couple of minutes. Okay. So our next big question is how to compute everything in atomic physics, all the atomic properties, and make them available. And here is the idea is that we have to, if we talk about the whole periodic table, we have to distinguish atoms by level of difficulty. And I know for the experimentalist, it's like, what is my laser wavelength? Like, do I have the laser in my lab, and how expensive would that be? In our case, it's how many valence electrons. So for us, it makes fairly little difference if we actually do computation for sodium or for cesium. It makes, so essentially it doesn't matter much going from top to bottom periodic table. It's more complicated, but not. It makes a difference actually going from left to right. So the more valence electron, the more difficult it becomes for high precision methods, just because same reason as quantum computing, you just have exponential scaling with number of valence electrons. So 1, 3, group 1, 1, 3 valence electrons, so the first 3 lines, we can automate. We know how to do this so well, I can literally push a button and the computer will calculate. So we automated the code for 1, we are automating codes for 2 and 3. So the idea is to compute everything which can be computed, to actually convert our research code into software. And we're actually working with computer scientists to do that, because it's a very different field out there when you actually want anyone to be able to run them, and when actually you want to run them with essentially no input. So you only input which electrons you want, which atom you want, and which property you want, and that's it, nothing else. Current atomic codes don't work like this. There is numerous parameters which you have to sort out what to put in. So 4 to 6 valence electron, we have first successful calculation of chromium, which we actually have a meeting tomorrow about it. We can do up to 6. 6 is complicated, 4 is reasonably easy. So that requires, probably could be automated, but requires some a lot of expert knowledge. And then the rest of it is sort of, black hole periodic table, middle of the lanthanides and actinides, and middle of the D shells, high field shells. We're actually developing codes to it. We have funding to do it. And eventually it's probably going to be AI. So we're probably actually talking to AI people because a brute force approach will not work here. So
data train.
Yes, we think we can train a neural network to actually select configurations. So, and that's what we are planning to do. So the idea is to do like computer calculate. Yes, question.
So what are you doing with correlate? I mean, naively.
Oh, we separate. So what we do core electrons. First, we create effective potential of all core electrons by couple cluster, extremely precise approaches. So the core electrons, so we know how to do core, and one valence electron. And we create effective Hamiltonian, which knows there is a core inside of it. And then we only have to correlate the valence electrons in that effective potential of the core. And yes, we could actually improve the core as well. In fact, this whole previous work, it actually will improve the core as well. So we can work in both directions. But core is usually not an issue, it's a valence electrons which is an issue. We know how to do the core.
And the back effect of valence electrons of core.
Right, it's because there is not that much, you start with a mean field. And there is any additional back reaction would be just in your correlation correction. It actually will be covered by the effective Hamiltonian. So unfortunately, when it's more than 6 valence electrons, we cannot do it. We actually have to do everything correlated directly. So which is a big issue here. So now we actually have the first version of our atomic portals online, all the alkalis and all alkaline earth ions. There are hundreds and hundreds of transitions there. It's very easy to use. Essentially, all you do is click buttons, and you can download all the tables. AC polarizabilities are in there. So if you haven't checked it out, then just it's UDEL Atom. It's kind of easy site, and it's all open access. So you just go in there. You don't need to log in or anything. And now we actually preparing the version 2 release, so it'll be much more extensive. So we actually want to have all alkaline earths, anything 2 and some 3 valence electrons, anything we ever published in highly charged ions would be there. If you have complicated atom, like if you have somewhere in your lab, you have table, everything I know about dysprosium or everything I know about erbium, put in the Excel, send it to us, we can actually put it on the portal. So we actually have ways of converting Excel tables directly into HTML. At this point, automatically, we only need references. So we can put other people's data in there. But for now, the question is, I would love to hear input from you. What we will release codes as well. Like, what ideas do you want? Like, for example, some people say that we want a light shift simulator, not just AC polarizability, but full laser polarization and do full light shift simulations. We probably can do it in the future. Also, the idea is that I have idea for experiment. Find me my atom or ion. Like I want this, this, and that. That's kind of idea. So we are 2 years in the project. We actually up to renewal shortly. So I'll let you know. We are looking for molecular theorists in the future, maybe to add molecular data in some way.
Yeah.
So I know there are some things out there. If you, I can forward you what it is. People have actually put some of the stuff online for ultra-cold, some of the ultra-cold molecules, some of stuff is online. So to summarize, atomic and nuclear clocks, it's a great potential for discovery of new physics. And we need new ideas how to use quantum technologies for new physics researches. We collaborate with particle physics. We would love to see more collaborations. And also, I'm sure I'm out of time. I want to talk about merely charged particles. We actually don't have time for it. That's something which is a completely new work. We haven't done anything about yet. We want to. But if you have an ion trap, remember your dark matter can hit your ion. So if you're interested, I'll be here, today and tomorrow. There are, I guess, a couple of lunches scheduled. We can talk about it if you're interested to collaborate. And I would like to thank all of you for listening. To all of our UD team, this is our online. Oh, this is our. I'm not sure what just happened. This is our online portal team. Yeah, dark matter particles can hit your ion. Yeah, it's not ultralight dark matter. It's a very heavy dark matter, and I can tell you why beam detectors actually blind to it. So this is our portal collaboration. We have one student graduate, another joint. Our other team, 2 senior research associate, a postdoc, and graduate students, and all of our many collaborators in the Q-Sense Institute, which I'm a PI on, and ERC's Energy Grant, and our code developers and particle physics collaborators. Thank you so much.
Well, I'm sure there's questions.
So I have a question. This is Bill Phillips again. You talked about how the coupling between the dark matter and the ordinary matter is going to cause oscillations in the fine structure constant, or at least it could, and that then this would show up as oscillations in frequency ratios in atomic clocks. What I'm wondering is, you probably said this and I just missed it. Are these oscillations because of a coherent coupling that causes populations or state vectors to oscillate, or is it because of the fact that you're moving through a wave that has galactic scale that causes the oscillation?
So what causes oscillation? Your dark matter wave will cause fundamental constants to oscillate. And just because that it could couple to your electromagnetic interaction. So think about this way, how do we define what electromagnetic interaction is? We have our Lagrangian and we have a coupling constant in front of our Lagrangian. And now suddenly we have an extra term, which is oscillating. So your alpha, it's previous alpha plus oscillating piece. And then all you do, you just plug this alpha in all of your normal quantum mechanics, and you end up with Rydberg constant, which have alpha square in it, then what actually will be dependent on your variation on your dark matter field. And again, Rydberg constant has dimensions, so we are very careful here. There are some very interesting effects when actually cavity does not respond, but clock respond, when you can actually see whether you can actually have variation from the actual value of Rydberg constant itself. But here, the main mechanism is that you do have a field which affects electromagnetic interaction affects the nature of electromagnetic interaction itself. And then you actually have oscillating part of alpha. And
right,
that affects the energy levels.
Right, but what I'm getting at is the oscillation because of the fact that I'm moving through a spatially varying dark matter field, or is it simply the oscillation that comes from having a coherent coupling?
Well, I think that I would define it as both, because you are moving through oscillating field. In this case, you actually are moving, so you do have some dark matter oscillation, and we can again talk about coherent or stochastic, and it is coupled.
I think you might not know that the mass of this field determines the frequency that it oscillates.
Yes. So the mass of the field determines exactly the frequency of oscillation. So oscillation frequency is fixed. It's so your cosine omega t omega is fixed by the dark matter mass.
Okay, so that sounds like it's a spatial variation. You showed that cartoon about riding through a
Sure.
wind of dark matter. That's the kind of thing that we're talking about.
Right.
So what's to say that the dark matter field shouldn't be moving with us?
Oh, that's actually very interesting, because dark matter is not rotating, or at least for all purposes, it's not rotating. It can't. The reason why the disk is rotating is because normal matter can radiatively cool. Dark matter cannot radiatively cool. So dark matter is just large blob around our galaxy. So it is what's called virially supported. So you have a random velocity of about 300 kilometers per second. But again, this is that's a total randomization. So the only really motion here is important for detection, that sun is moving around the galactic center at 230 kilometers per second. For all purposes, we consider dark matter stationary in respect to that motion.
So that pretty much assumes that the dark matter doesn't couple enough to the normal matter to get it moving, and that it doesn't come to equilibrium.
Okay, so it interacts with it gravitationally. So what happens, actually, you would not have galaxies by now if your dark matter did not interact with normal matter. So gravitationally it does. But for the rest of interaction, it's an open question. How does it interact? So here we assume that there is a coupling.
Right, but not big enough to make the dark matter rotate with the ordinary matter.
Definitely not. Right.
Okay.
So yes, we assume it could be, there could be slight rotating component, but I don't know enough about to actually be. So we have no evidence at this point, and we could be in dark matter stream. I mean, that could be a whole different. We do not know dark matter distribution in our galaxy. Period.
Yeah.
We want to measure it, and I see the question from Ron here. Yeah. So we okay. I would love to discuss further if you want further this question with you. So. Yes.
Yes, I mean, as I understand it.
Yes.
The distribution, the density distribution, and perhaps the flow of dark matter, whatever it is in our galaxy, particularly in our galaxy, is not well determined, and there's quite there is indirect evidence that long ago there were dwarf galaxies and other sorts of things that passed through the Milky Way and quite possibly created streams and flows, and there may be other phenomena that create kind of density variations. You can say things on a very large fraction of a galaxy scale, but as you get down to the kiloparsec scale, something like that, or below, there could be large variations in what the density is. We might be in a dark matter deficit accidentally now, or over density region, this kind of thing.
Okay, so the comment was that yes, we do not know the dark matter density, and we do know average dark matter density to the galaxy, which is a 0.3 GeV per centimeter cube, and that's about let's say one hydrogen atom per few cubic centimeters here. So. And that's, by the way, dark matter does not affect the motions of planets. There's just not enough for it. Now, we could have extreme overdensities on Earth. For example, merely charged particles which are strongly coupled will thermalize on Earth and they'll get stuck on Earth. We could have dark matter halos. All of it is a completely theoretical constant. We do not have measurements of. By the way, what we need extremely good frequency comps, and we actually need to be able to determine accelerations of bodies in our galaxies to, I think, 10 to the minus 10. And then we can actually get the dark matter distribution. We will eventually, but we don't know it now.
I point out also there's some new ideas. I've been part of some of them, but others
too,
to use naturally occurring clocks like pulsars and things like this distributed through our galaxy, and the chirp of binary pulsars relative to us, remarkably over long periods of time, over years, that chirp can give us the local acceleration. And if you have enough of these pulsars scattered around, kind of like a GPS system, but now intergalactic within our galaxy, it can give you information more directly without it assuming Gödel's theorem of what the dark matter distribution is, because basically what the gravitational potential landscape is in the galaxy. And remarkably, existing pulsar data accumulated over many years is good enough. We just published a paper in Physical Letter showing this. Take one pulsar relative to the Earth, get a measure on the average dark matter density that is that is statistically significant and agrees with the measurements made by astronomers from velocity measurements over many decades, and is close to the same precision level, just losing one pulsar. So I think it's a very exciting opportunity to try to hopefully get even more pulsar data and then use these naturally occurring clocks analogous to the human manufactured clocks, but they're out there very far, great distances away, scattered throughout our galaxy. So that's a cool synergy with, natural man-made clocks.
Right. So it's a great comment that you can actually probably get dark matter distribution from pulsars data. And another thing, if dark matter clusters on Earth, and if it's scalar dark matter, if there is some sort of screening effect by Earth or various scenarios, then all you need to do, you need to send the clock to space. And I'm involved in some of the white papers. If you're interested to be involved in the clocks to space, there is a NASA, or actually any quantum sensors in space, there's a NASA decadal survey looking for white papers until October 1st. If it's a mission paper, I think there's a longer deadline for it. If you want,
walk-in customers here at JQI seminar, the kings of queens. How about one more from the audience before we break for lunch? Yes, sir.
So is this effect where the presence of mass is changing a fundamental constant? Is that true for matter in general, or is it something special about dark matter?
So the question was, whether the presence of mass would change fundamental constants. It could in principle, but in this case, it's a very specific dark matter scenario. It's ultralight scalar dark matter, and that assuming it's linearly quadratically coupled to your electromagnetic interactions. So in principle, yes, there are various scenarios. For example, if you go back to the question of dark energy, we know that it has to be screened on Earth. So there has to be some mechanisms that field, and there are chameleons, galleons, other thing. We do not see dark energy as a fifth force on Earth, because dark energy could generate, if it's a field, if it's not a cosmological constant, if it's a field, it would generate kind of a gravity-sized force. And we're pretty sure we haven't missed one on Earth with an enormous amount of experiments. So in this case, that would be a mass-dependent effect. In a gravitational field, it actually would be screened. There are some dark matter scenarios in which dark matter will be screened on Earth as well. So the mass could affect it, but in this case, it's a different effect. That just because you have a field which affects fundamental interactions. It's in its really initial level.
And so that's something that we're sort of like, that's the way that we've designed that field. Is that it?
Well, it's actually pretty generic. If you have a scalar particle, there's only so many ways you can couple to Lagrangian. So it's pretty much just a normal quantum field theory of how you can couple. All you need to know whether it's a scalar, pseudo-scalar vector. People kind of run out of the steam at this point, and then we know the couplings to normal matter. So there are very specific ways of how you can couple any generic dark matter to standard model, and there you can do it, through portals. You can couple through Higgs, through dark photon, or through vector bosons, or through neutrinos. So it's not that, and that's all been actually in our review paper, it's written out how any generic dark matter can actually couple to quantum sensors. There are some very specific type of effects you're looking for. So this is not just, it's not random, it's just a field theory.
One last one, 140 characters or less. And so, if understood well, this sensitivity comes from the fact that the transition is very narrow in the atom, right? But it's also true that the narrower the transition, the harder it is to interact with it because of the laser capabilities. Is that a fundamental limit in the transition? Okay, so the question is whether sensitivity is connected to how narrow the line is, and the narrower the line is to actually whether it's more harder to interact with the atom. This is actually not quite the case. So sensitivity has nothing to do with how narrow the line is. It has to do with how close your probe electrons sit to your nuclei. It's a sensitivity to alpha, it's a relativistic effect. So normally your normal valence electron in all the clocks normally sits about a few atomic units away from the atom. Like, okay, the maximum distribution for this electron. What you want that's why sensitivities are small generally. So what you want to be, you want this electron which actually probes variation of alpha in your clock, be closer to the nuclei. That's why highly charged ions, okay, nuclear clock is a whole special different scale. But highly charged ions, the sensitivity is simply because your electron sits closer to the nuclei, because highly charged ions are small. The electronic cloud is small. But to answer your question of whether having more and narrow line would create a fundamental problem, surprisingly, the answer is no. Terbium Plus has, I think, 10 years lifetime. The question is,
how much laser power are you going to shine on it to excite your clock transition, and whether this causes stark shifts. So they've been ideas of how to avoid it, and Ytterbium 3 plus clock, Ytterbium 3 clock actually avoids those shifts. There are special schemes of clock probes which actually allows you to work on extremely narrow lines.